this video I'm going to be doing another optimization problem, and in this case we're talking about volume. So the question reads, an open rectangular box with square base is made from 48 feet squared of material. What dimensions will result in the box with the largest volume? So the first thing I did was I drew the diagram so it's easier to visualize. Notice how the base, since it's a square, has the same dimensions for its length and width. So I labeled those X and X, and the height we don't know, so I labeled that as Y. So right now we want to write our known and unknown equations, and remember for our known equations, the known normally has an actual number at the end of it. Notice we're given that the only number we're given is that there's 48 feet of material used, and that means that's signifying surface area. So our known equation has to relate with surface area. So if you write our equation, notice for surface area that we have to exclude the top part because it's an open box. So let's take account of the base. So that's x. The area of the base is x squared. The area of just this portion would be xy, but there's two of them. Remember this and the back. So plus 2xy. And again, we have to take care of this side and that side. This side is xy, so we have to multiply that too. So plus 2xy again. And remember, this equals 48. If we simplify things through, we get x squared plus 4xy equals 48. Now we can write our unknown equation. Remember, the unknown equation is normally the one we want to maximize. In this case, we want to maximize the volume, so let's write it as v equals. In this case, the volume equals x times y, so that's x squared y. So notice that what we want to do is we want to take the derivative of the volume and set it equal to 0, so we can find the coordinates at which it has the largest. But we can't take the derivative of the volume because we have two variables to the right of it. So we need to make this right side of the equation somehow into one variable. So we either need to substitute x in terms of y or y in terms of x. However, in this problem, substituting y in terms of x is much easier, since in the unknown there's only one y term, but there's two x terms to the left. So let's do that. Let's solve the known equation for y. So if I bring that over here, and I subtract x squared, I get 48 minus x squared equals 4xy. Now y equals this divided by 4x, so 48 minus x squared over 4x. So now what I need to do is I need to substitute this into the volume equation. If I do that, I get v equals x squared times 48 minus x squared over 4x. If I cancel stuff out, this 2 becomes a 1, this x goes away. So this equals x times 48 minus x squared over 4. If I multiply things through, this equals 48x minus x cubed all over 4. So again, remember, the volume equals 48x minus x cubed over 4. And what we did to get that is we solved this equation for y and substituted that in for that y, and we simplified and we got this. So remember, we need to take the derivative of the volume and set it equal to 0 so we can find the x dimension at which the volume is the maximum. So let's set that equal to 0. So 48. So no, actually we have to take the derivative first and then set the derivative equal to 0. So we need to find v prime. So in this case, we can simplify this and we can make this. If we put the forward of both these two terms, we can make this 48x over 4 minus x cubed over 4. And now we have to take the derivative of this. So again, the derivative of this would be the derivative of that minus the derivative of that. The derivative of 48x over 4 would be 48 over 4 minus the derivative of x cubed over 4. Remember, we would bring down the 3, keep the 1/4, and subtract 1 from the exponent. So negative 3 over 4x squared. This simplifies. Actually, let's set this equal to 0. So we're going to set this equal to 0. So 0 equals 48 over 4 equals 12. Minus 3 over 4x squared. Remember, we have to solve for x squared to subtract 12. Negative 12 equals negative 3 over 4x squared. Multiply both sides by negative 4. 48 equals 3x squared. Divide by 3. 16 equals x squared. Take the square root of both sides. X equals plus or minus 4. So now we got our dimensions as x equals plus or minus 4 to maximize the volume. However, we cannot assume that x equals 4 or x equals negative 4 is the actual dimension that maximizes the volume, so we have to prove that using the number line test. However, notice that we cannot have a negative dimension, so the only thing we have to test is positive 4. So So in the previous step, we noted that at x equals positive 4, that the volume is maximized. However, we still have to prove that. So let's draw 4 feet at a number line test. And remember, we have the test points left and right of it to prove, we have the test points left and right of it and use the signs to prove that it's a maximum. So remember, we're testing points in the derivative function. So we have to look at this. So if we take, for example, if we take 0 and plugged it in for x, notice how it's a positive number. So upsloping line. Pick the point right of it, like 10. Notice how this portion of it outnumbers that, so this would be a negative number. It's downsloping. Notice it looks like a mountain and a peak, so it is indeed a maximum. So at x equals 4 feet, the x dimensions at 4 feet, the box's volume will be maximized. However, we're not done because it's asking for all the dimensions, so we need to find the y dimensions. So we know x equals 4 feet, but we need to find what y equals to complete the problem. So notice that our known equation is x squared plus 4xy equals 48. And again, all we need to do is plug in 4 in for x and solve for y to get our y dimension. So let's do that. So we have 16 plus 4 times 4, y equals 48. Subtract 16, we have 32 equals 16y, and y equals 2 feet. So at x equals 4 feet and y equals 2 feet, the volume of the box is maximized when we're given the constraint that the surface area of the box is 48 feet squared. So again, that is our answer. Thank you guys for watching, and please comment and subscribe below.